In the first tutorial, we got familiar with GNU Radio Companion interface. We've seen how to handle real quantities and imaginary quantities, addressing such awkward values as negative frequency, imaginary voltages. We characterized the properties of a low-pass filter, and we showed how we could introduce our own Python code in the generated GNU Radio Companion Python program. However, we emphasized that the Python code could only interact with scheduling and the connection of the various blocks and not on the IQ stream. Now in this tutorial here we're going to consider how we can read the IQ data, and we're asked to fit a Gaussian function on this IQ stream. So to continue on the previous tutorial, we had our blank sheet here, and we had a Python snippet where we could execute code inside this Python snippet over here. If we want to have a bit more extensive piece of code, for example, for reusing some older Python libraries, we can have a Python module, and this Python module can be much more extensive, since now in an editor we're going to have the freedom of writing as many lines as we want. For example, we can define a function whose arguments might be callback functions, and in this infinite loop we're going to say, well, let's wait, for example, 1 second, and sleep is part of a time library of Python, and when we're finished sleeping we can actually print an output. Now this piece of code will be run indefinitely, and the main scheduler of Qt is already running, so we need to execute as a new thread. So we import time to be able to sleep, and if this has to be a new thread, now in this Python snippet we're gonna import threading so that we can create the new thread. In the newer GNU Radio Companion, this might be created automatically at the beginning of your program, and we might want to create the new thread, calling, here we see it's called EPY module 0, so we're going to call as a target the function found in EPY module 0, and it was called myfunc. We provide the capability of killing the thread when the calling function dies, and to do this we must demonize the thread, and we provide as arguments the callback function, so the setter and getters generated by GNU Radio Companion. It's a list. Finally, we call this with a start function to launch, and with this we have now the capability of launching the thread generated in the EPY module. And if we run this again, we need to save this in a Python compatible name, so to be able to run this. When we run this code, we see that once every second the display appears here, and if we stop, the thread is indeed killed because it was demonized. How do we now interact with the IQ? So first of all, let's create some new data. So we create an additive white Gaussian noise, which is going to be a floating point with an amplitude which we want to be user tunable, and because this noise source is 0 mean value, we're going to add a mean value as a constant, which we are going to call the average, and is a floating quantity. We now know that when we want to change a variable to have interaction with it, we're going to call it the amplitude from 0 to 1 with a default quantity and a step, so that we can change the amplitude of the noise, and we're going to Control-C, Control-V the same with the average value over here, which is also something with a mean value and the maximum minimum. Now we're going to display the frequency domain, so the spectrum, because a noise should display all the spectral components with the same amplitude. It's a noise, so all spectral components should be represented with the same weight. And because the amplitude is going to be a Gaussian, we want to display the histogram. Again, these are all virtual, so we must add a throttle block in order to be able to slow down the rate of data and make sure that the computer is not overloaded in our execution. So what you see now that we execute this flow graph, we have something that looks like a Gaussian and a flat spectrum. This is not very beautiful. We want to maybe improve a little bit. So say that we're going to put in our histogram sync 65,000 samples, and let's make a bin a bit sharper. So let's make 1024 bins. And if we execute this to have a sharper histogram, and similarly if you middle click button and we do some averaging, then we see that indeed the spectrum includes all the possible frequencies. We have a mean value of 0.2. If we change the average value, we see that the mean value is going to shift as we are changing the mean value over here. And on the other hand, if we change the standard deviation, which is the amplitude of the noise, we see that increasing the amplitude will broaden the Gaussian and make the standard deviation wider. So this is a clean Gaussian noise, and we would like to have some sort of signal processing for identifying the properties of this noise. This requires that we create a new Python block. So if we search on Python block over here, we get this guy, and we have an input and an output. If we double click, we can edit the properties of the Python program. So we see here the name, which matches the name of the Python block appearing over here, and we have the input and the output type. So we're going to change these properties. So initially it's complex numbers. We see that it's blue input and output, so we want actually to have real quantities here. And maybe we don't want to display an output which is input multiplied by a constant, but we'd rather at first display the length of the vector that are provided. So we can print the length of the first vector first, because we have one input over here, so that's input number 0. If we had multiple inputs, we would have a vector with more elements. Now the console of GNU Radio Companion is rather slow, so what we're going to do is we just say that if the variable that we're incrementing here is more than 100, then we're going to display in order to avoid overloading the console. So with this example here, we can at first check. So you see that the type here was changed to orange, and if we rotate by left arrow so that we can put the input next to the output over here, we need to output the result somewhere. So we're going to use the Qt number sync and Qt GUI number sync, and this will allow us to display the output. So if we run this guy, we're going to see that it displays the number of elements that are shared by the scheduler with a program. And what you see here is that you're not allowed to make any assumption on the number of elements provided by the scheduler. Sometimes it's 1192, sometimes 1186, and then 4. So it's really dependent on the scheduler state and on the previous block state. So if we want to compute a histogram, we cannot afford having a variable number of data coming in our block. So we need to convert from stream to vector. So stream to vector is this guy over here. We rotate it with left and right arrow so that the output is on the left. It's a floating number, and we want 1024 sample to calculate our histogram. So this output goes to this input here, and now we need to feed our custom block with a vector. And to understand how to do this, we relied on the online tutorial about Python blocks with vectors, which explains that we need to add in the definition of the input type the scalar definition and the number of elements in the list. So let's do this. We say that we replace the example parameter with vector length over here, which we take as 1024 elements, and we're going to make here a list of vector length element, and we get rid of all the everything that refers to the example that was here earlier. So now we're going to receive vector length element, and we're going to display the length of input item 0. So let's see how this goes. So now we connect the output of one vector to the other. Actually, this is a parameter that we have here, vector length, but be aware that the manual online tells you that you're not allowed to dynamically change, because if you change dynamically this and the vector length in the program here is given as a static number, then there will be a conflict in assessing the consistency of the flowchart when checking with the output over here. So that's not going to work. Now, if we run this flowchart here, you see that we actually get our histogram with a flat value, and now we have something that says 2, 4, 8, 1. So this is actually the number of vectors accumulated in the input over here. So we ask for vectors 1024 element long, but there is no reason that the scheduler would give us one vector of 1024. We've seen earlier that sometimes we get 8192 samples. So now what we actually can do is, if we have more than one vector, we can loop on the element that we have received. So we can, for example, for k in range of 0 to the length of input item 0, so that will be all the vectors that we have received, and we can ask what is the length of the kth element of item 0. And if all goes well, this should show us 1024 sample for each one of the elements. And indeed, we've got vectors which are all 1024 sample long. So this is very important, because now we can access each one of the vectors that we were given, and these are the values that we wish to fit. So in order to fit with a parabola function, so remember that a parabolic function is something that is expressed as a function of input x as an amplitude times exponential of minus the x input value minus the mean value squared divided by 2 times the sigma, the standard deviation squared. So this is the expression of a Gaussian function, and this is what we would like to fit. So we're going to define a fit function, which is what we would like to find, which is dependent on 3 quantities: the amplitude, the mean value, and the standard deviation. And in order to perform the fitting, we must return, as requested by SciPy, the calculation of this function, so the exponential of the received input value, which will be the second argument that we receive here, of minus the x minus the mean value, and the power in Python is Eisenfortran star star, divided by 2 times the standard deviation squared, and this will be the return function of our fit function. In order to be able to do the fit, we need to load from SciPy the scientific Python and its optimized toolbox. We need to load the curve fitting. So now we have the optimized function, which is the gradient descent needed for identifying amplitude, mean value, and standard deviation as a function of this guy over here. And now we need to feed this function. So we've understood how to access each vector. It will be input number 0 and the kth vector from the length over here. So now we're going to ask to get the histogram from this input noise, the histogram from input items of 0 and k, which is what we just saw as being the 1024 long vector. We say how many bins we want and the range of the input. So because the noise is supposed to be between -1 and 1, or actually GNU Radio works with values from -1 to 1, we can calculate the vector over here. In addition to calculating the vector, we wish to fit the curve. So let's first check that this calculation here works, just to make sure that we go step by step. So at this point, we see here that the thread is running, and we calculate our histogram. Of course, we cannot see it at this point, but at least the histogram calculation is working correctly. Now we would like to do a curve fitting, and we'll see that it's not going to work, but let's give it a try first. So we search for the optimum parameter that we wish to find from the curve fitting, and the curve fit function will take as argument the fit function that we just defined over here, and x and y. You can optionally provide the initial values for the parameters, so in our case amplitude, mean value, and standard deviation. If you don't provide here the initial values of the parameters p0, then all parameters will be initialized as 1. This will not work because when we do the calculation of the histogram x value provides us with the bin coordinates, and the bin coordinates are the beginning and the end of each bin, so that we have 33 x values, which are the beginning and the end of each bin, and only 32 measurements, the content of each bin. So we must actually calculate the center point of each bin, and this is simply done by saying let's try to take the average of the beginning, so from the x position from the first element to the last -1, and we take the mean value with the second element until the end. So by doing this, we have n-1 element because we've removed the last one and removed the first one. We take the mean value of the x, which is the middle of each bin, and now we can do a fit function on this x and y, which have the same number of items. So now we see that Python is no longer complaining, so now we can finish our calculation by printing the quantity of interest, which are, we print the, so it's a f function that we're going to display, and we display the optimal value item number 0, which is not the most interesting one because this is the amplitude, which is related to the number of sample and the number of elements that we put in the bins. More interestingly is the optimal value number 1, which is the mean value, which we can relate to the second parameter and the mean value that we change. So every time we only display 2 floating point numbers because otherwise it would be too long and it's going to change size as we do the calculation. And finally, most importantly, the standard deviation, which is what we're really interested in. So we print this quantity, and actually we're not going to do this anymore for a finite number of n, so we just stop incrementing n to just run this continuously. And if we run this example now, we see that we are going to display the mean value, so the amplitude here, 36 is not very important. The mean value and standard deviation, 0.2, 0.2, are working pretty well. So here we have the outputs, and if we run this while changing the parameters, we can check actually that if we change the mean value over here, we have here the 0.2 value. We changed it to 0.03. So let's let the display done. So here we have the 0.3. And actually on the standard deviation, you see that sometimes we have minus 0.2 and sometimes we have 0.2. Now the reason is in your flowchart, we only have sigma squared. We never have sigma. So depending on the initial condition and the type of noise, we might have sometimes the positive and sometimes a negative square root of sigma. So what we can do is always display the absolute value so that we're sure that actually we always have a positive value. And if we run this, and for example, we increment the amplitude, so the breadth of the noise over here, so for example, to reach 0.5, and when you kill the flowchart to dump the display over here, we're going to see that the standard deviation indeed reaches the 0.5 which we just calculated, and you see that now the quantities are always positive. So we have a mean value 0.2, the standard deviation that reached 0.5, always positive because we took the absolute value. So this is the output of your custom processing block, which now can access the IQ stream. This is the big difference with what we had earlier. This was all done with synthetic data. If you wanted to run this on real data, Well, all you would need to do is to replace synthetic data with a file source so that you can look at your recorded data. And if we do this, it has to be a floating point number. Here we have loaded a data file that was provided by GSI staff so that we can repeat the same analysis, not on synthetic data, but on real data that had been recorded by hardware software-defined radio. And one challenge when considering data file is usually they are rather voluminous data. You see here that it's a 134 megabyte data set that were provided, and that doesn't tell you anything about how these data have been stored. If you just look at the binary file here that was provided, it just all looks like random quantities because it's all floating point or integers or bytes. There is no way of knowing from the data file what is the file format. So what GNU Radio is promoting is to use a meta format, and this meta format is, for example, a SIGMF, so signal meta file. This is for a different file. This is a GPS data that was collected, and you see here, for example, you will find in such a meta file the sampling rate, which is exactly the same sample rate that we had in our flowchart, and the way the data are stored. In this case, for example, it's complex interleaved 8-bit integers, so 8i for integer 8-bit, C for complex, and when it's a complex in interleaved, and then a few additional meta information that are not directly used in the flowchart. So whenever you're storing some binary data in a SIGMF data file, make sure to also save a SIGMF meta. In the final tutorial, we're going to address how to make GNU Radio exchange data with external software or distribute on multiple processing platforms.